Okay, good afternoon. And first of all, thank you to the organizing for giving me the opportunity to be here. And I will talk about antineutrinos from the Earth, present status and future perspectives. Here the outline of my talk. First, I will describe briefly what are the antineutrinos from the Earth, and then how can we measure these antineutrinos. Next, we will see briefly the result from Camland and Borexian experiment and their implication on a geological point of view. Next, a few words about neutrinos as predicted by Earth models, and finally a few words about the future. Before continuing, I have to mention my colleague from Ferrara, Fabio Mantovani, Gianni Fiorentini, Marica Baldoncini, Virginia Strati, Gerti Zita, and Ivan Calegari. In particular, I remember everybody that Marica Baldoncini here present a poster during the poster session. Okay, a few historical news. The neutrinos were born on board of the Santa Fe chief train. I don't know if everybody knows this history, but in 1953, during the experiment at the Hanford reactor, Reines Cohen found out high background unexplained, and Gamov tried to explain this unexpected background by this letter here. And Gamov wrote, "It just occurred to me that your background may just be coming from high energy beta decay members of uranium and thorium families in the crust of the Earth." But, next, Reines promptly answered to Gamov, and the answer is here. Heat loss from Earth's surface is 50 erg per centimeter square per second, and if assume all due to beta decays, then have only enough energy for about 10 to 8 1 neutrinos per square centimeter per second. This is the first estimate of antineutrino from the Earth. A slightly bit higher estimation. Okay, let us see what are the neutrinos. The radioactive elements present in the Earth's interior, mainly uranium, thorium, and 40 potassium, decays, and here I report the result of the decay chain of uranium-238. The result is lead-206 plus 8 alpha particles and 6 antineutrinos. For thorium, here is the result of the thorium decay chain, and this is the case of potassium 40. Here also we report the main characteristics of this decay chain, the maximal energy of antineutrinos here, the Q value, the number of antineutrinos emitted per second and per kilograms of uranium and thorium and potassium respectively, and the watt per kilogram emitted here. So one can observe that Earth emits mainly antineutrinos. A rough estimation of the antineutrino flux from the Earth is 10 to the 6 antineutrino per square centimeter per second. This number is quite similar to the flux from boron neutrinos from the Sun, but Earth shines through antineutrinos, whereas the Sun shines in neutrinos. Next, a fraction of neutrinos from uranium and thorium, not from potassium, are above the threshold for inverse beta reaction. Here you can see the maximal energy from uranium chain, thorium, and potassium. Next, neutrinos originating from uranium and thorium can be distinguished through their energy spectrum. For example, antineus with highest energies are from uranium, as I already mentioned. Finally, I remember that a unit, useful unit for measuring the neutrino signal is a terrestrial neutrino unit, which means one event per 10 to the 32 free protons per year. in 1 kiloton of liquid scintillator we have about this amount of free protons. As an example, I reported here the complete uranium decay chain. Here, here, starting point and the end point. We have alpha decay, this diagonal, and beta decay, the horizontal line. 98% of uranium geoneutrino signal comes from just two transitions, this one and this one. And here also I reported the spectrum of the geoneutrinos from uranium decay. As you can see, this spectrum is a sum of several beta decays. These two are the main, give the main contribution. And it is important to note that this spectrum is essentially as a result from a theory estimate. How can we detect antineutrinos from the Earth? As well known, this is a crucial detection reaction, and we have a underground detector, liquid scintillator detector, who collect geoneutrinos from the Earth. Here is a list of present experimental setup, Kamlan, Borexinon, and future experimental SNO plus is planning. But there is a problem, because our detector collects also antineutrinos from reactor. In fact, reactor antineutrinos are the most important source of background in geoneutrino detection. So let's spend a few words about these antineutrinos from reactors, and I recall that more details are presented in this poster. Okay, reactor antineutrinos and geoneutrino spectra are partially overlapped. Here there is a sketch of a reactor spectra. About 30% of event is between 1.8 until 3.3, the so-called geoneutrino windows. I recall you that the maximum geoneutrino energy is 3.26 MeV, and about 70% of reactor signal is in this high energy region. So reactor signal in the high energy region is crucial for modeling the reactor contribution in the low energy region, and therefore is crucial for extracting information on geoneutrinos from a total antineutrino signal. So we need to calculate with high accuracy the reactor antineutrino signal, and this calculation requires several ingredients concerning production, propagation, detection of antineutrinos. And I observe also that the reactor signal changes along the time according to the different reactor operational conditions, whereas the geoneutrino signal does not change along the time. Here I present a worldwide map of reactor antineutrino signal we have obtained recently in this paper by using the most updated data information about production, propagation, and detection of reactor antineutrinos. The total uncertainty, the estimated total uncertainties from this expected signal is of the order of 3%. But only a few words about this. Not only over the world, we can calculate the signal also for particle sites here, where experiments are presently running, Borexinon and Kamlan, or sites where experiments are planned, like SNO Plus or Juno, or future experiments are discussed in the literature. I don't want to enter into the details of this number. I only want to mention that we are able to calculate the expected reactor neutrino signal in the total energy range here, in the low energy region, and if we compare this is a geoneutrino signal expected for these different sites, we can make the ratio R in the low energy region over G, and so we obtain a sort of parameter which can indicate which site is best for the geoneutrino detection. More details can be obtained if you want to see this website which we have prepared. Now let's come to the results. Up to now, we have two experimental results, one from Borexino experiment at LNGS here in Italy, and the other from Camland experiment in Kamioka mine here in Japan. The Borexino data taking period extends from concerning geoneutrinos extend from 2007 until 2012, and they collect 14 plus 4 minus 4 geneutrino events corresponding to a signal of 39 plus minus 12 TNU. Camland operated for a long period, about 10 years, and then the geneutrino events are of the order of 100, corresponding to a signal of 30 plus minus 7 TNU. Now, let us see what can we learn from this experimental data. I start from an historical point of view. In this plane, S signal, expected signal TNU, and here on the x-axis the heat flow from the Earth in terawatts, and this point represents the prediction for different Earth models, starting from the pioneer works by Heder and Marx in 60, next other publication 1991, 1984, and the more recent one which covers this area. We can see that if we put in this graph the result of Camland and Borexino, we can see that we have an indication about that the modern model of the Earth are preferred. Now let us come to some open questions about natural radioactivity in the Earth. First, what is the radiogenic contribution to terrestrial heat production? Next, how much uranium and thorium are present in the crust of the Earth, and how much into the mantle of the Earth? Next, if there is something hidden here into the Earth core, a georeactor or some potassium. And finally, is the standard geochemical model called BSE, bulk silicate Earth model, consistent with the geneutrino data? And let we see if geneutrinos can help us to give an answer to these questions. Since from geology's analysis we cannot get address answer to these questions for the following region. First of all, the deepest hole in the Earth is about 12 kilometers, so we have as a surface of the Earth, not in the interior. Next, we have samples from the crust and the upper portion of the mantle are available for geochemical analysis, and other important information are from seismology reconstruction of the density profile. Density profile, not the composition of the Earth. Here a sketch of the different layers we have into the Earth. CMB is not the cosmic microwave wave, obviously, but is a core mantle boundary. So this is a core, this is a mantle, and next several layers in the crust. Concerning geological information, there are some news recently. There are some recent paper which gives a refined geophysical structure of the continental crust, I mean this layer here, and new compilation of geochemical data. There are also a new approach for evaluating the composition of the middle crust and lower crust, and the contribution from the lithospheric mantle. Here is not lithospheric mantle, a small portion of the mantle can be addressed from classes of different models. Okay. Let us see how Camland result and Borexino results can give information about the radiogenic heat. A useful way of representing this is a plane as signal versus heat. In this plane we can draw two lines, red and blue line, and the region in between this line contain all geological model consistent with geochemical and geophysical data. This region represents our knowledge or our ignorance about geochemical and geophysical model. In particular, in this figure, a particular class of models are indicated here, 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 and this model different one from each other from the different abundance of uranium and the ratio of thorium to uranium. Okay, if we draw, just a moment, okay. If we draw the best value, for instance, for Borexino here, plus minus, it is there. Okay, here and here, we can find the intercept between this line with this geological region, and we can, this is only a sketch of course, we can find out that the prediction from Borexino about heat, radiogenic heat, is from 10, let's say 10 until 38 terawatt. The same can be, of course, done for Camlan. And what we know about the heat from the Earth? Debate about the terrestrial heat flow is still open. Here there are several values present in the literature. There are values spanning from 31 until 47 terawatt. So the range is quite large. In particular, this determination is the most recent determination, which is based on 40,000 holes. Here in the picture, here you can see the hole. Each point is a hole, and is based also on a study about the heat loss through the seafloor. And here you can see that we have a great part, the major part of the heat coming from the ridge, from the continental ridge. These models roughly predict that the radioactive contribution to the total heat flow is about 7 plus 13, so about 20 terawatt. This is a prediction from the model of the Earth. And let us see what this is the result derived from Camlan and Borexino, as I mentioned in the previous slide. At the moment, you see this number, at the moment we cannot derive a definitive conclusion, but I wanted to remark that this is the first time that we can test a model of the Earth. Okay, now let us see how we can have a look into the deep Earth, I mean the mantle. If you want to extract global information brought by geoneutrinos, the contribution from regional geology, regional means a region of about 500 times 500 kilometers squared around the site of the experiment, has to be controlled. For each element, uranium and thorium, the expected geneutrino signal S in one site on the Earth's surface is the sum of three contributions. Local means this region quite around the detector site, from signal from the crust. These are the signal coming from the rest of the crust all over the Earth, and next the mantle. So we can derive as a mantle by knowing the total signal measured by the experiment and by subtracting the contribution of the crust. This is done in this paper here, 212, but in this paper the results refer to previous results from Camlan and the Borexino measurement of geneutrinos. Here, if we use the most recent result from Borexino and Camlan collaboration, I report here what we have found. For Camlan, this LOC means regional contribution to the signal. This FFC means the rest of the crust of the Earth. so we have this number for the total crust signal. We subtract, these are the result, 31 minus 25, and this is a signal corresponding to the mantle. The same exercise has been done also for Borexino result, and these are 6 plus minus 7 for Camlan, then 15 plus minus 12 for Camlan. Clearly this is not quite a significant result, but this is the way we have to done to obtain a result. Now let us come to the neutrino signal around the world. Here is a map of all the world from this reference of the expected neutrino signal according to this model of the Earth. And let us see where the experiments are located. Here is Borexino, here Camlan, and for Borexino, the signal, the 68% of the signal come from the crust, the rest from the mantle. Similar occurs also in Camlan, 70% from the crust and about 29% from the mantle. Concerning future, in Sudbury, here in Canada, the expected neutrino signals is 74% from the crust, 26% from the mantle, and for Juno in for Juno in South China, 71 from the crust and 29 from the mantle. One can see that in all these places, the contribution from the crust are quite similar, and consequently also from the mantle. So this experiment can address information mainly about the crust. If you want to obtain information about the mantle, you might move to another place, here in Hawaii, for example, where the expected neutrino signal is mainly due to the mantle. Here you can see that the detector placed in Hawaii corresponds to a signal of 72% coming from the mantle. Now let us spend a few words about the most recent determination of neutrino signal, because a big effort has been done in this calculation in the last 3 years, about it. And as I've already mentioned, the expected signal is obtained by some 3 contributions: the local region, the rest of the crust, and the mantle. So, concerning Camlan, a detailed analysis of the local region, means this region, a square of a 500 kilometer side, you can find here as a reference. And so one can calculate the contribution to this local region deriving from local geology, subducting slab, crust of the Japan Sea, and find this number, about 80 TNU. The rest of the crust give about 7 TNU. And concerning mantle, this contribution to the most upper part of the mantle, continental lithospheric mantle, a small part of the mantle, is estimated here. And then for the mantle, this is only a result of a model calculation, okay? And the total predicted theory, the total predicted signal is here, plus minus 1 error. I want to stress that it's very important to give an error to this number. And it's not easy, because in this error enters the geological measurement, but also a geological model of the Earth. And we have to compare this with experimental data. The same exercise has been done from also for Borexino. We can see here the region around the local region around Gran Sasso laboratory, and we have this region is particular since there is more sediment respect to Camland region, and so the exercise is the same. We can calculate the local contribution, the rest of the crust of contribution. This contribution for this thinner layer of the mantle and predicted mantle from the model, and this is the result to be compared with the experiment. Concerning the future, also for SNO+, a study has been done. Here you can find the reference. And the local region around Sudbury has been divided into 7 nominal lithological units, you can see here. And about 3,000 samples has been used for estimating uranium and thorium abundance in the upper crust. And finally, has been built a 3-dimensional geophysical models, we hope quite accurate, and these are the results. At the moment, we have only theoretical prediction, and we are expecting the experimental data. Finally, I will spend a few words about Juno experiment, planned to start in 2020. And here I will show you the result. This result from this paper. In this figure, you can see the cumulative signal contribution to the Juno detector coming from neutrinos. The different component. We have in blue the mantle, in green the continental lithospheric mantle, and in red the crust, all the crust. And we can see that the 50% of the total signal comes from uranium and thorium in the crust, in the region within about 800 kilometers from the detector. So we can consider this region, this local region, and if one look into details the contribution from each sector, one can see that this sector, named T2, gives the contribution of about 27% of the total. And these are based on models and all measurements of the geological point of view. So a new survey of this region is quite recommended. So let's conclude with this observation about reactor antineutrinos and neutrinos in Juno. Here you can see the expected signal in Juno coming from reactor. In red, the signal, calculated when we consider the Yangjiang and Taishan nuclear power station on. Here in cyan, in blue, the expected reactor antineutrino signal, where if the Yangjiang and Taishan were switched off, and in green the neutrino signal. One can see that if these 2 power stations were off, Juno will become an excellent experiment for the neutrino measurements. I mean that I don't want to shut down the nuclear power plant, but if happens that for some maintenance or something else, or some delay in the starting operation of the nuclear power station, one can use Juno to detect neutrinos. So here are my conclusion. Neutrinos represent a unique probe for study the Earth's interior. Up to now we have 2 independent experiments, far 10 to the 4th kilometer each other, measuring a neutrino signal in agreement with expectation. A big effort in neutrino signal calculation has been done in the last years. Future experiments are needed to better determine the radioactive content of the deep Earth, and so we can conclude that neutrinos means a fruitful collaboration between geologists and physicists. And I want to recall that in June there will be Neutrino Geoscience 2015, a great opportunity to go further with this type of study. Thank you.
Thank you very much. Thanks for the talk. Are there questions? these surveys that they're going to do, are they hard to orchestrate, these surveys near Juno, or are they?
I don't know. We have to ask.
No, yeah, so we are discussing with geologists, but there's no concrete plan how to do that.
I know that there are contacts between geological people. I don't know. Wait.
No more questions? Let's thank Barbara again. Okay, our next speaker is Kristen Buck, and he's going to tell us about double show.
Okay, thank you. Now the background of the previous presentation will become the signal in my talk, so it's a pleasure for me to present you at this nice place here the latest results and the current status of the double-show reactor neutrino experiment. So reactors are a strong and pure source of MEV electron antineutrinos, and this makes them a good location to do neutrino disappearance oscillation experiments. And we can classify the present and past reactor neutrino experiment basically into three categories according to their baseline between detector and reactor. So we have the short baseline experiments at a distance up to about 100 meters from the reactor. And here what was observed is a neutrino rate which is lower than in the prediction, which is not expected in the three neutrino framework. So this is what typically is called the reactor neutrino anomaly. Then at larger distances, so at 10th of kilometers, we have the Cumberland experiment, which is sensitive to the solar parameter, the mixing angle theta 1, 2. And in between, at this first step here, we have the currently running theta 1, 3 experiments, which are double show, Diabase, and Reno. So the nice thing in this experiment is that they provide a pure measurement of theta 1, 3 with no parameter degeneracies and no matter effects. And so I think it's very important to get a precise measurement of this value and also redundant measurement with different experiments, since this will be an important input parameter for future experiments measure other parameters as leptonic violations and things like that. So this is the double show site. We have two reactors and two detectors. The far detector is at the site at the laboratory of the original CHO experiment that was already running in the 90s. This is operating since April 2011. And now since last year, we also have our near detector operational, which is at a distance of average distance of 415 meters. So this is measuring the unoscillated detector flux, and then this is close to the first minimum in this survival probability. So here's a comparison of the different site configurations of double show with the other experiments, Reno and Diabase, and you see there are substantial differences. So in double show we just have two reactors. There are advantages and disadvantages of that. The disadvantage, of course, is that we have rather low statistics compared to the other experiments. But on the other hand, it helps with the systematics. So the flux uncertainty we can keep very low with two detectors in such a simple configuration. So there is a recent publication from this year where you can find more details about the flux uncertainty for the different site configurations. This is the double show collaboration. It's an international collaboration with more than 20 institutes and about 120 people. A large fraction of them you can see here in the picture, which is was made in front of the entrance of our near laboratory. So for the first years of running, we just had our far detector, so we were relying on the precise knowledge of the prediction of the expected neutrino rate. And to have that, you need to have a good knowledge of the reactor parameters and of course also of the number of protons in our target. And so the prediction is basically limited by the mean cross-section per fission, this number here. And here we use the Bechet anchor point as normalization to keep the uncertainty smaller. This is something that was already done, for example, in the CHO experiment. So the neutrino detection happens in a liquid scintillator detector. So we have the inverse beta decay of the antineutrino, which creates the positron and the neutron. and then you get a prompt event with at least 1 MeV energy due to the annihilation of the positron, and then a delayed event after several microseconds due to the neutron capture either on gadolinium or on hydrogen in our liquid scintillator. Of course, the capture on gadolinium has some advantages, so the coincidence time is about a factor 6 shorter compared to hydrogen, and the energy is much higher, so we are at 8 MeV, well above the typical backgrounds of the natural radioactivity. But nevertheless, we also succeeded to do a theta-1,3 analysis with neutron captures on hydrogen. So this is our detector design. So we have in the center our target scintillator. This is a gadolinium loaded liquid. So the gadolinium is added in form of a beta diketone complex. The target is surrounded by the gamma catcher, which is an unloaded liquid scintillator, and the purpose of this is to capture gammas from the IBD reaction that might escape the target volume. And then finally, the third part of the inner detector is the buffer liquid, which is a non-scintillating oil, which acts as a shielding, basically. And this inner detector is optically separated by a steel vessel from our inner VTOR, which is a liquid scintillator as well. So this is a difference compared to other detectors of that type, which often use Cherenkov detectors. And when we talk about the correlated backgrounds in the experiment, you will see the advantages of using this liquid scintillator. And then finally, we have 15 centimeter of steel shielding, and on top outer VTOR of plastic scintillator strips. In addition, we have several calibration systems in our detector. So we have a LED light injection system that can be operated at multiple wavelengths, and then we can deploy radioactive sources. So we use cesium, germanium, cobalt, and californium as neutron source. So for the target, we have this vertical Z-axis system where we can deploy sources basically anywhere along the central axis. And then in the gamma catcher, we have this guide tube, which has this shape. So we can also deploy sources along this path here. So here, this slide is summarizing the evolution of the theta-1,3 results since the start of the double show experiment. So when we started data taking with the near detector, which was April 2011, the situation was that we had first hints from other experiments on non-vanishing value for theta-1,3. There was the T2K result, for example. And then double show in the same year, at the end of 2011, first presented from the reactor side indication for non-zero value of theta-1,3. The year after, we got the results of Reno and Diabay, which basically confirmed the double show result, but at much higher precision. The same year, we presented the first analysis with neutron captures on hydrogen as a cross-check. Then in 2013, we published our RRM analysis. I will come to that later. And the near detector, or the laboratory for the near detector, was delivered in this year. And last year, there were also some analysis updates in all the experiments. And there we first published a spectral distortion in our neutrino spectrum, and we started the data taking with the near detector. So in the following, I will basically describe the analysis done for this publication in 2014, and the improvements compared to the previous analysis, which was in 2012. So the first improvement was on the energy scale. So for the energy scale, we have different corrections and calibrations we do. First, we correct for non-uniformities inside our detector, so we do these maps to do this. Then we correct for time variations, and we look into the non-linearities. And after all, this is what we basically get. So we have in the end a very good agreement between DART and Monte Carlo for the different calibration points. But not only for the absolute energy, but also for the energy resolution, which is plotted on that scale. And the total uncertainty of our energy scale that we obtain in the end is lower than 1%. Then for the neutrino selections, there were also many updates. So we have, as before, a mu and VTOR. Then we have these so-called light noise cuts. So this is light emitted from our PMD basis, and we require that basically the signal is uniform in space and coming simultaneously, more or less. These cuts were optimized. Then we have, for the correlated background reduction, several cuts and vetoes, and part of them are new in this analysis. We also have, for the first time, use a distance cut to further reduce accidentals. And then for our energy ranges and for our coincidence time window, we basically opened our cuts. So this was possible because we had all these additional background reductions, and now we could open our windows, which is good for the efficiency. So it allows to increase our efficiency and at the same time reduce the uncertainty of it. So here in these plots, it's clearly visible what these improvements basically do. You see in the signal region we have basically, so in yellow, this is what we had in the 2012 analysis, and the black dots are from the new analysis, and here on top you always see the reduction for the different bins. And you see in the signal regions there's basically no change, but in the regions where we are background dominated, for example at high energies above 10 MeV, we get this strong reduction due to basically a purer signal. And you also see this for the delayed energy here in this low energy region, and for the correlation time. So in particular at the very short delta T times, you see the effect of the reduction of the stopping muons, which have this short time scale, which are strongly reduced with the new cuts. So this is what we get for the signal with the new selection over time. So you clearly see the three different reactor conditions that we have here with both reactors on, where you get about 50 events per day, and then half of it with when there's one reactor off. And then we have these two short periods where both reactors are off, which are very valuable in terms of measuring our background rate. And so these are the number of events that we measured in this data taking period between April 2011 and January 2013. And you already see from the rate that we get less candidates than predicted without oscillation, which is due to the theta 1-3. For the detection efficiency, so this is basically the uncertainty on that is dominated by the neutron detection efficiency. All the other efficiency are close to 100%, and the neutron detection efficiency was determined using Californium data in the target and along this z-axis, and also in addition we use the IBD candidates in the full target volume, and finally we achieved to get a total uncertainty on that of 0.6%. So this value is dominated by the uncertainty of the gadolinium fraction, so the fraction of neutron captures on gadolinium with respect to other elements as hydrogen, and this will basically cancel with a near detector because we have the same chemically the same target liquid in our near and far detector. So now I come to the backgrounds. So the backgrounds we classify into three different types. So first we have the accidentals, the accidental background. These are basically random coincidences where you have single events that randomly fall into the time window and the energy windows of our IBD signal coincidence. And so for this is the prompt spectrum that we obtain, and you see here this basically cuts off around 3 MeV. So this is basically above the thallium where the natural radioactivity ends. And we find a constant rate of 0.07 events per day that can be measured with high precision using off-time windows. And if you compare this to our signal rate of about 15 neutrinos per day, you see that this is basically a negligible background. Already a little bit more critical are the so-called correlated backgrounds. These are fast neutrons and stopping muons. So stopping muons, there are some chance that the muons can enter the detector from the top through the chimney basically, and is not seen by our outer veto and also not seen by our inner veto. And then if it stops in the chimney and then decays, and then the Michel electron basically gives our delayed signal. And so this is one type of correlated background we have, and but this is effectively identified in our new analysis by the PMT hit pattern, which is significantly different than for the standard IBD events. Then the second correlated background are fast neutron events, so they can be created in the rock outside the detector by muons, and then there is some chance that they enter the detector. They do make recoil protons, which give the prompt signal and are eventually captured on the gadolinium or hydrogen. And this background is extrapolated from the rate at high energy. So we have good reason to assume that this background is flat in energy. So we made this flat extrapolation, so that the flatness was basically confirmed by the. So we have a method to detect these fast neutrons by using the in vitro information. So sometimes the protons also deposit some energy in our in vitro. Now this is where it becomes important that we do not have the Cherenkov detector but the scintillator here. And from this in vitro detect events, you also see in the low energy region that we have a spectrum which is consistent with flat. Then another type of correlated background are cosmogenic isotopes that can be produced by muon spallation. So the most famous of this is probably the long-lived beta emitter lithium-9. So this is not tagged by our muon veto, which is only 1 millisecond, but the lifetime of these isotopes is on the 100 millisecond time scale. So we estimate this type of background by fitting the time correlation of the IBD candidate and the previous muon. We have also for this background a dedicated veto. This is our lithium veto, where we have a likelihood that takes into account the distance of the prompt event to the parent muon track and the number of neutrons produced after the muon. So if you produce a lithium-9, you normally also have in this event some neutrons coming with the muon, and we use this information to get additional rejection, and the rejection of this veto is more than 50%. After subtracting these vetoed events, we get about 1 event per day of this background, and this is the dominating background in our experiment. So for the backgrounds, we have a very important cross-check to measure our background model basically. This is something unique in double show, so we have periods where both reactors are off, and in total we have here 7.2 days. So the residual neutrinos that you would expect from the simulation in this period is just 1.5 events, and the observed events are after all the vetoes 7. So this is a little bit lower than in our background model, but it's consistent with 1 point something sigma. So we use this off-off data not only to confirm basically our background model, but we also use it to constrain our θ13 fit. So here in this table I summarize the uncertainties of our experiment. So as expected for the far detector only phase, we are flux dominated, so we have this 1.7% from the flux, and all the others are lower. For the background, I would like to say that this is basically before the fit, so from the fit, this uncertainty is further constrained and gets smaller, and the statistic is at the moment no limitation for the far detector, but for the near detector, this will be the limiting uncertainty for a long time, maybe even until the end. So this is the result of our rate and shape fit. Sine squared to θ13 is 0.09 plus 0.032 minus 0.029. This result is in good agreement with all our previous publications and also in good agreement with the results that are found in Reno and Daya Bay. So now I will come to a rather hot topic in this area, I would say. So if you plot the measured neutrino rate versus over the predicted one, then you get something like that. So you see several features here. So first, of course, you see this dip here around 2 MeV. This is expected if you have a positive θ13. So this is basically this θ13 dip. And but then in addition, you have some excess in this area between 4.5 and 6 MeV, and maybe also some deficit here. But for sure, this excess here is the most significant. So now the question is what is the origin of this excess? First, one could think this is some background we did not account for. But if it would be background, what you would expect is that this excess is basically the same, independent of the reactor configuration. So if you have 1 or 2 reactors running or no reactor running, and but this is not what we see. What we see is that the excess is correlated with the reactor flux which disfavors this background scenario. And in addition, we also have the reactor off-off data, which is even lower than our prediction, what we measure there. So also from the reactor off-off, there's absolutely no hint for that this is a background. Second possibility would be, is there something wrong with the energy scale? If it would be energy scale, it would be basically flux correlated. But to get an effect like that, you need a rather strong deviation from our energy scale, and we have no reason to assume that deviates like that. So, of course, most of the calibration sources are at rather low energy, at least for the single gammas, but we could confirm in this region or validate our energy scale by using neutron captures on carbon. So in that case, you get single gammas of 5 MeV, and we find very good data-to-Monte Carlo agreement there. And also for the boron-12 spectrum, which is a beta emitter that extends up to 13 MeV, we do not see any features like that in this area. So also energy scale is disfavored. Then the third possibility is there something with the flux prediction? This is something currently under investigation, so we will have a presentation tomorrow about reactor neutrino flux, and I think there it will also address this issue. So this is also seen in other experiments, so we will see what we will have in the Reno and Diabate talk on this topic. So, but I would like to emphasize that this effect has no significant impact on our θ13 measurement, since this is basically outside the energy region where the oscillation happens. The robustness of our result is also confirmed in a rate-only analysis. So we have this so-called reactor rate modulation analysis, where we compare the observed versus the expected neutrino rate for different reactor power conditions. So we have basically 3 points for the 2 reactor on and 3 points for 1 reactor on, and then in some cases this for both off. And this is a pure rate-only analysis which does not rely on any spectral information and is even completely independent of any background model. And we can extract a θ13 and the background rate just from the linear correlation doing fit, and you get basically by the slope the θ13 and by the intercept the background. And here are the results for different configurations. So if we leave the background completely free, so this is the case where we are completely background model independent, you see that we get basically the same result as in the rate and shape fit. And also for the background, we get the same number as from our background model. However, the sensitivity in this case is not very good. If we want to improve the sensitivity, we can add the reactor off data point, and you see then we get here higher precision, so we get consistent result a little bit lower. This is because in reactor off we have rather few background events. And then if we want to get the best sensitivity out of this rate-only analysis, we can use the background constraint, and then we are almost as sensitive as in the rate and shape, and we get the identical result. So there is also some physics beyond θ13 that you can do with double show, but I think I will skip this for time reasons. So now a few words on the near detector. So at the last Neutrino Telescope 2 years ago, the situation was that the near lab was even not yet delivered. At that time, our goal was to start data taking in 2014, and we succeeded to do so. So the near detector construction started in May 2013, and a little bit more than 1 year after that it was filled, and the data taking started last December. And here is some very preliminary first result. So here you basically see the energy spectrum from spallation neutrons. On the left you see it for the far detector, on the right for the near detector. There's one very important difference here. For the far detector, this is calibrated data with a full calibration. For the near detector, it's completely uncalibrated, so we did not calibrate for any inhomogeneity in the detector and things like that. But nevertheless, you already see the similarities, and I think this already demonstrates the feasibility of the IBD measurements. So you see here the gadolinium peak, the hydrogen peak, and even the carbon peak of the neutron captures in the spectrum. Some preliminary study of the near detector signals also indicate that from the background viewpoint everything is fine. So we have a similar rate as in the far detector. So this means that our radio purity and shielding goals were fully achieved with both detectors. So this is the projection of the sensitivity. So our last analysis with the far detector only was basically after about 2 years. Now we are at this point here. And you see in black, this would be the sensitivity with the 2012 analysis, and now with the new analysis, you see basically the improvement of sensitivity. The projection is that after 3 years of running, we should be about 0.015 for the 1 sigma error, and this basically assumes that there are no further improvements in the analysis, but we think there is even some potential to go lower than that, and in the most optimistic scenario, we might go down even to 0.01. So this is the summary. So the recent analysis, we have analysis improvement with the far detector only analysis that I presented. So we improved the accuracy of the energy reconstruction. We optimized our selection and reduced the detection systematics. We have new background tagging and rejection techniques applied, and we included the reactor off-off data point in our fit. So we get this result here. We have some independent cross-check analysis, for example, the hydrogen analysis, which I did not present in this presentation. There will be an update on that soon. And we have this rate-only reactor rate modulation analysis. And the near detector data taking started last December. Thank you.
So you said that the 5 MeV excess you see in your data doesn't affect your theta-1,3 measurement. But if you use only one detector to measure theta-1,3, I think it affects your result.
Yeah, we tested this, basically in two ways. One check is, for example, is RRM analysis, which doesn't use the spectral information, and this gives the same result. This is one confirmation. But also for the rate and shape fit, we did a test where we basically allowed for an artificial background in that area and let this flow. And then if you do the fit with that, we get basically the same result. So it's not very different. So in this region, the statistics is not very high. And so the main information for the oscillation is basically around this 2 MeV, and what happens there is much more important for the fit.
Maybe you don't have enough statistics. I mean, your statistical error is big in 5 MeV region. Maybe that's why. Because when you do shape analysis, the error bars are covering.
Yeah, the high square of the fit is not that bad. Yeah, this is if you look at the single bins, the error is not that small. Yeah.
Yeah, you mentioned how with the near detector now, you'll be able to remove that dominant systematic uncertainty from the reactor flux. And your next largest uncertainty looks to be the lithium backgrounds. Is there any potential for reduction of that uncertainty?
Yes, for sure. So, of course, statistics helps also for this background. So, it would be very helpful if you have more reactor off-off as well. But also by just adding new data, this should improve. But it's true that I think for the efficiency, most of the uncertainties we have will cancel with the near detector. So besides statistics, probably the dominant uncertainty will be on the backgrounds in the beginning. Yeah, that's true.
Thank you very much. Our next speaker is on to talk about
You think they're all on Okay. So good afternoon, everybody. It's a really nice sunny day, and my name is Sunny Seo. Here. And so I will talk about new results from Reno. But first of all, I would like to thank you very much to the organizers for the invitation here. This is my third time in Venice, and it's always good to be here in this nice, beautiful place.
So this is a quick overview of my talk. So I will talk about Reno results using 800 using 800 live days of data. And the new result is we updated our sine square 2 zeta 1 3 measurement since Neutrino 2014. So we have a new rate-only result. And there are two types of analysis. One is neutron capture on gadolinium, and the other is neutron capture on hydrogen. And next, I will talk about our shape analysis status. And our delta M square measurement is almost done using shape analysis. So we are currently checking our systematics. Do you have any other pointers? Because this doesn't work very well.
No.
Okay. Our spokesman's apology to the our chairman of the conference, Mauro Meggetto, because our spokesman promised that we will announce our delta M square measurement in this conference, but we decided that we will check our systematics more thoroughly. So we apologize to you. And then finally, I will talk about the observation of 5 MeV excess, which was also introduced by a previous speaker. So Reno collaboration, we have 11 institutions and 40 physicists, all from Korea. We are Korean collaboration, but we are really welcome you. So for our future project like Reno 50, please join us. You are really welcome. So our project total cost is about $10 million, and we started in 2006. And we are the first reactor experiment taking data using two detectors, near detector and far detector, since August 2011. And this is our collaboration photo. And so Reno location. So this shows our South Korea, our Korea here, and China you see here, and Japan here. And Seoul is, thank you. And this is Seoul, and this is Yonggwang. Yonggwang means glorious light, which is somewhat reflecting neutrinos. And so this is about 4 hours driving distance from Seoul here, and this is Pyongyang, North Korea. So if you go to Yonggwang, we have this 6 reactor cores here, and total thermal power produced by these 6 reactors are 16.8 gigawatt. Okay, and we have 2 identical detectors. One is near detector, about 300 meters away from the center of this reactor core array. And the far detector is about less than 1.4 kilometers away from the center of the array. And those 2 detectors are built under small hill, so it helps us to remove this muon induced background. So the overburden is about 120 meter water equivalent for near detector, and for far detector is 450 meter water equivalent. So this shows our Reno detector. This is a schematic view, and it is a cylindrical shape. Actually, it's 4 cylinders here, and the innermost cylinder is a target. Okay, it has a 16.5 ton liquid scintillator with 0.1% gadolinium loaded, and the radius of the cylinder is 1.4 meter, and height is 3.2 meter. And this target is surrounded by gamma catcher, which has a 30 ton liquid scintillator. And the gamma catcher is surrounded by a buffer, which has 65 ton mineral oil. And where we have PMTs here, and there are total 354 10-inch PMTs attached in the buffer region. And the outermost cylinder is a water BITO region. It contains 350 ton water there. And where we have also PMTs of total 67. 10-inch, the same type of PMT. So this is a real photo of our detector. There are cylindrical, 4 cylinders of a detector. So detection principle of reactor neutrinos. It's an inverse beta decay, process. So our previous speaker in WC here already explained to you. So I just skip this. And so for identifying this inverse beta decay signal, we have two types of signal, prompt signal and delayed signal. So prompt signal it shows here, and delayed signal when the neutron is captured either on gadolinium or either in hydrogen capture. So depending on where it captured, it has a different signatures for the delayed signal. For the gadolinium capture case, the peak of the energy of the signal is about 8 MeV, and while hydrogen capture is about 2.2 MeV. And the time separation is also different between the two. In this case, it's about 30 microseconds, the mean time, and in this case, hydrogen capture case is about 200 microseconds. So we can do parallel analysis, independent analysis on either gadolinium or hydrogen. Okay? So by requiring energy of prompt signal and delayed signal, and also the time requirement, coincidence requirement, we can suppress our backgrounds a lot. Okay? So Reno status. Reno has started data taking from August 2011 with near and far detector, and average DAQ efficiency is about 95%. And this plot shows you our DAQ efficiency as a function of time. And this is for the near detector, and this is for the far detector. And this vertical line actually is the daily DAQ efficiency. And this black line here is the average DAQ efficiency. Okay? And you see different colors here, A, B, and C. But this represents the data which we used for our zeta-1,3 measurement. So using a period of data, we announced our first measurement of sine square 2 zeta-1,3. A sample data is about 220 live days of data. And this was announced in 2012 in Neutrino conference in Kyoto. And B data sample is about twice of A data sample, slightly less. So 403 live days of data. So we improved our zeta-1,3 measurement using this data set. Not only the statistical improvement, but also systematic uncertainty is reduced. And for the C data set sample, this is twice of B data sample, so it is about 800 live days of data. And so my talk will talk about the data using C data set. Okay. And so C data set is here, but our current status is here, data taking status here. And our estimated neutrinos up to now is about 1.5 million neutrino events in the near detector and 0.15 million events in the far detector. So since we have a lot of neutrino events, we can do absolute reactor neutrino flux measurement well. And also we can study reactor anomaly and strial neutrinos as well. So this is a neutron capture by gadolinium signature. So this is delayed signal at the far detector. And the data is the black with the error bars, and Monte Carlo is the red histogram. So data in Monte Carlo matches pretty well for the far detector and near detector. And this one is the delayed time distribution. The neutron capture on gadolinium, how far away from the prompt signal is captured. So the measured value for the far detector is 26.09 plus minus 0.28 microseconds. For the near detector, it's 26.16 plus minus 0.09 microseconds. So within error bars, they agrees well, which means we have identical detector, which supports the statement of we have identical detectors. So this slide shows you our, just kind of a quick summary of our rate-only analysis result. So at the beginning, I told you that we improved our zeta-1,3 measurement since Neutrino 2012, 2014. That was done by reducing our background systematic errors by applying new cut criteria. And especially for the lithium-helium background, we have reduced about 30%. And also Californian contamination, this is only special to our experiment. We reduced by 35%, okay? And so there is one thing to note that is background estimation. Our background estimation is based on, data. It's data-driven, so it's not Monte Carlo. So this means when we take more data, it's not, we improve our statistical error, but also systematic error. So it's good for us. So backgrounds. So this table lists up our backgrounds, accidentals and fast neutrons and lithium, helium, and californium contamination. And this is the total. And there are two values actually here. The previous values are from our Neutrino 2014 result. But after then, we changed our cut criteria, especially Qmax, Q total cut. This is a little bit technical, cut, so only the reactor people knows what this means. And by, this value we changed 0.03 to 0.04. And by doing this, we allow more accidental backgrounds, but at the same time, we allow signal events in the lower energy region. So by doing this, we can minimize any bias to the spectral shape in the lower energy region. So this is especially done to do our spectral analysis, okay? And so I don't read up all these things, but the final number, total background in the near detector, we have 18 per day. For the far detector, 3.6 per day of background events. So the fractional, this background quantity is about 3% for the near detector, and for the far detector, this value is about 6%. Okay. And this pie chart actually shows you the uncertainty for each background, okay? So for the near detector, the lithium helium background really dominates our near detector backgrounds, while for the far detector, we have some californium contamination. So californium is dominating, and then next one is lithium helium. And other backgrounds are relatively small compared to lithium helium and californium. So this plot shows you our measured spectrum of IBD prompt signal. So this is for the near detector, and this is for the far detector. So as you can see, the background level is really small here, and this is for far detector. So this inner plot is the log scale of this to show you how much background we have here. So total IBD candidate for the near detector is about 460,000 events, and while in the far detector is 46,000 events. So in this plot, what it shows is our observed IBD rate per day after background subtraction, 10 minutes, okay, as a function of time. So the data points are, with the black dots with the error bars here. And there are two lines here. The red one is expected with no oscillation, and the black one is expected with the oscillation using best fit sin square 2 theta 1 3 values. So for the near detector, it's hard to distinguish between this red and black because the oscillation is really small. For the far detector, you can, easily distinguish between this black and red. So our data points in the far detector, you can see it matches well with the expected with the oscillation hypothesis here. And you see all these bands here, that what it means is that we have 6 reactors, okay? So, depending on how many reactors are up, it shows tent-like behavior here. So we have a very good agreement with our observed rate and prediction from this plot. So here in this plot, what it shows here is y-axis, it's observed IBD rate after background subtraction, and x-axis expected IBD rate with oscillation using best fit sin square 2 theta 1 3 value. So this, ideally speaking, this one should show one-to-one relations. If we, observe 500 events, the expected one should be 500, for example. So this blue dot with error bars are from our near detector, and these black ones are from our far detector. So when we fit this with the function ax plus b, we get b is 0 and a is equal to 1. Okay. So b is equal to 0 means our background subtraction is done well. Okay. If the b is not 0, you didn't subtracted your background well enough. That's what this plot means. Okay, so new theta 1 3 measurements by rate-only analysis. So using 800 live days of data, our measured value sine square 2 theta 1 3 is 0.090 plus minus 0.008 statistical error plus minus 0.008 systematic error. So maybe some of you may notice that in Neutrino 2014, our value was mean value is 0.101 plus minus total error 0.013. So about 1 sigma level was reduced in the mean value. Okay. So using this 0.09 value, if we combine with the T2K data, we have a better chance to determine delta CP, which if delta CP is 3 pi over 2. Okay. And in this table, what it shows is the first one is our statistical uncertainty, which is for the near detector and far detector values, and the ones inside of these red ones represent our systematic error components, each components. Okay, I don't read all these things, but this pie chart actually represents our systematic, uncertainty. So most systematic uncertainty we get from backgrounds here. This is our backgrounds. And the next one is detection efficiency and isotope fraction, equal amounts they contribute. And the last one is thermal power. So this is the milestones of our sine square 2 theta 1 3 measurement from the Neutrino 2012 to until now. So we have about 8.2 sigma significance. And this was released about 2 weeks ago in Singapore. So energy calibration and 5 MeV access I will talk about. And this is a kind of summary, and I will show some plots later. And we are confident in our energy calibration. So systematic uncertainty on spectral analysis is well under control. And since we are confident in energy calibration, we are confident in the 5 MeV excess. Okay? So the 5 MeV excess means we observed about 2% excess compared to the model. Okay? And it has a strong positive correlation with the reactor power. And this means we need a re-evaluation of reactor neutrino model. Okay? So this 5 MeV excess is explained by additional several fission isotopes. And you can, the Dan Dwyer and Tom Langford wrote this paper, PRL paper, and then we'll give a presentation tomorrow in the morning session. So he will talk more about this. So energy calibration from gamma ray sources. So this is for the near detector and this is for the far detector. So we use radioactive sources, germanium and cobalt, and this is polonium beryllium. And there is a neutron capture on hydrogen and neutron capture on gadolinium. These are from the IBD events in our data. So each point has a well-known energy. Okay, so when we measure our photoelectrons, we can make this kind of plots, and then we fit these our data points, and using these fitting functions, when we convert photoelectrons to energy. Okay, so using this conversion function, we can apply how well it works. So we applied this for our boron 12 backgrounds. So boron 12 is an unstable isotope. They are produced by muons. When muon passing through our liquid scintillator, it smashes carbon and producing boron 12. Not only lithium helium, and these are unstable, so it decays and produces electrons. Okay, so this is electron spectrum from boron 12, and the near detector data is a triangle, open triangle here. Maybe it's not very easy for you to see here. And for the far data, this is a blue dot with error bars here. So near data and far data, they matches pretty well. And also our prediction, Monte Carlo prediction, is here in the histogram here. So all three, near data, far data, and Monte Carlo prediction, when we use our energy conversion function, they match well. If our conversion function is not done well, they do not match. Okay, so we are pretty confident about our energy calibration. And this bottom plot is far divided by near, so you can see it's aligned to 1. Okay. So 5 MeV excess. So Here, what is shown on the top plot is our prompt spectrum. Okay, the data is dots with error bars, and the Monte Carlo prediction is the blue histogram. So Monte Carlo prediction, we use 2011 Huber and Miller model. At the 5 MeV excess, using this plot, it's not easy to see there is excess or not. So we made this plot. This is in the y-axis is the data minus prediction divided by prediction. So you can easily see the excess in the 5 MeV region. The excess amount is about 2.2%. Okay, in the near detector, and the far detector it's about 1.8%. But within error bars, they matches. Okay, we need more statistics in far detector. So here, the near detector, I said it's of 2.2% excess with our uncertainty. This 0.4 experimental uncertainty plus minus 0.49 from the expected shape error from this paper. Okay, so even though we include this expected shape error, the significance of this 2% excess is about 3.6 significance. Okay. If we use only our experimental uncertainty, it's more than 5 sigma excess. Okay. For the far detector, we have less significance, of course. So for this 5 MeV excess, actually we first mentioned in 2012 Kyoto Neutrino conference. Okay. This is the slide which we used. Exactly, I didn't change anything. At that time, we said the expected IB prompt spectrum from the Reno MC do not reproduce the shape in the energy region of 4 to 6 MeV. At that time, we didn't know what that is, but now we know what that is. It's due to reactor neutrino, those 5 MeV excess. So more about 5 MeV excess. So in this plot, in the y-axis, it's a 5 MeV excess rate per day. Okay, and x-axis is our total IBD rate after background subtraction. So this is positive correlations. That means that this 5 MeV excess is related to reactor neutrino component. It's not background. If it's a background, it should be flat. Okay. So this is another plot showing that the 5 MeV excess is related to reactor thermal power. So there are two types of colors. One is red and the other is blue. And blue is the total IBD in terms of as a function of the time. And the red one, the blue one, you read this y-axis IBD rate per day. And for the 5 MeV excess, you read the left-hand side. Okay. So as you can see, IBD rate changes. But also the 5 MeV excess changed in the same pattern, right? So this is another, proof that the 5 MeV excess is a reactor neutrino component. So shape analysis status. So our time scale measurement is almost done, and systematic uncertainty is well understood and well under control by now. And we will soon publish our paper very soon. So stay tuned. And this plot shows you our prompt signal. For the far detector data is this black with error bars here. And this blue histogram is from using our near detector data. Using near detector data, you expect how many events you see in the far detector if there is no oscillation. That's the blue one here. Okay, but this orange line is. But if we apply our best fit sine square 2 theta 1, sine square 2 theta 1 3, then it becomes this blue becomes this orange. Okay, so it matches well between far and best fit oscillation using near detector data. Okay, and in the bottom plot is far data divided by prediction without oscillation. So you see, energy dependencies here. So these values will be determined soon, and it's coming from the shape analysis. And this plot shows you our, L over E plot. In the y-axis is, electron anti-neutrino survival probability as a function of L over E. And this is this blue is our near detector data, and the black with error bars are from our far detector data. And this orange color represents prediction from our near data using best fit oscillation. Okay, so it matches well with our far data. So hydrogen analysis. So this is the last. So hydrogen analysis is an independent zeta 1-3 measurement, and we improved since Neutrino 2014 by better understanding of our background. Okay, so this is our delayed signal. It makes a peak around 2.2 MeV, and this is the delayed time distribution here. What we measure is about 207 microsecond, and also far detector 206 microsecond, but within the error bars they matches. And this is actually event vertex distribution for this type of neutron capture on hydrogen event. So this is a target area, and this is gamma capture. In gamma capture, we don't have any gadolinium. So hydrogen capture analysis, this hydrogen capture occurs mostly in this region. For the target, there is a gadolinium, so gadolinium capture is dominated. So you see less event here. And these are, kind of summary for, our analysis, but you read it later. Using hydrogen capture analysis, sin-square 2 zeta 1-3 value, we measured is 0.103 plus minus 0.014 statistical error, and for systematic error is the same as statistical error. Okay, so it has improvement from the Neutrino 2014, where we have a 0.025 systematic error here. But this is only using 400 days of data, but now we are working on 800 of data for this. And this is our prompt spectrum for the near detector, and this is far detector. These are background levels. So compared to gadolinium analysis, we have much more background here because the time delay is about 200 microseconds, which is much longer, so we are more contaminated by backgrounds, especially accidental backgrounds. So Reno's projected sensitivity of zeta 1-3. So this is our current measurement, 0.09 plus minus 0.008 plus minus 0.008. So the significance is 8.2 sigma. And within 3 years, we can, push down this current total error 0.011 to 0.005. And this will make about 18 sigma significance. Okay, and this plot is actually shows you our, total uncertainty in our sin-square 2 zeta 1-3 measurement from the beginning to, until now. The current point is missing here, but total error is 0.011, so it should be around here. Okay, so our final goal is, once again, if we use rate plus shape analysis, it's a 5% precision. Okay. So this is a brief history of zeta 1-3 measurement, and I don't want to, go through, but our current value of Reno using 800 rate-only analysis is here. So summary. So we observed a new reactor component at 5 MeV with a 3.6 sigma significance. And new measurement of zeta 1-3 by rate-only analysis is here. And shape analysis for the time scale is being finalized, and stay tuned. And our first result on hydrogen capture with analysis result is here. These two measurements are consistent within error bars. And our goal is we want to measure sin-square 2 zeta 1-3 with 5% accuracy within 3 years. Okay, and this will provide the first glimpse of delta CP if accelerated results are combined, T2K. And stellar neutrino search I have mentioned in this talk, but this is ongoing, so stay tuned. So this is really last. This is advertisement. So some of you already know that. So we are planning for Reno 50, after Reno. It's like Juno experiment. So currently we are not funded, but we have we got 2 million grant from Samsung. And so for 3 years. So this will be used for R&D of liquid scintillator purification and high quantum efficiency PMT performance to reach 3% energy resolution at 1 MeV. So Reno 50 really needs you. We don't want to have a Korean collaboration, so you are very, very welcome to join us. And there is a poster, is there. So thank you very much for your attention. Yes.
So you said that your H13 measurement went down by 1 sigma.
Yeah.
But so it went down by 1 sigma, but most of the data is in common. So does that mean the new data went down a lot more?
What do you mean? New data that went down more? Because we applied the new selection criteria. That's the main reason. And, within error bars, our previous measurement and current one is all consistent.
I see. It was
Yeah.
mainly the change in the analysis
Yeah.
that reduced the value.
Yeah. It's the it's the same. Yeah.
Could you show back the plot where you have the structure at 5 MeV with both the near and the far detectors? Yeah. So it seems you have also an excess at low energy in both detectors. So
In both detectors.
yeah, a structure at 1.5 MeV in positron prompt energy.
Yeah. Good
What is
eye. We are investigating this whether this is related to reactor thermal power or not, but as you can see, statistics is very small, so it's hard at this stage. It's hard to say this is reactor related or not.
And when you say it's reactor related, I mean, imagine you have an effect in your detector, like an energy scale effect. Then the excess, if it would be the case, would scale with thermal power. So it's not, I mean, when you say that since the excess is scaling with the reactor power, it is obviously due to reactor, this is not correct. So it just excludes backgrounds, but it leaves open two solutions, either a detector bias selection or reactor neutrino flux. But you cannot
you say
claim,
because
you cannot
of
claim
this
that
point.
we have demonstrated with this data that the effect is due to reactor neutrino fluxes.
I mean, this plots clearly shows correlations with reactor thermal power. If it's a background, it's not proportional to the
Sure, but it can be a bias in the energy scale, for instance.
bias in the energy scale.
Yes.
But if there is a problem in our energy scale, as I show you as an example for the boron 12 spectrum,
So, and for the energy scale, how do you correct for non-uniformities, for instance?
we correct non-uniformities. For the gadolinium analysis, we don't see big ununiformity. It's quite even. But for the hydrogen analysis, we notice that there are the uniformity is not quite good enough compared to gadolinium. So we apply uniformity, charge correction factor for the space.
Do I understand well that you don't correct for non-uniformities for the gadolinium analysis? You don't.
We don't, because for the gadolinium analysis, we see uniform distribution.
But you have no calibration source, for instance, in the corner of your detector. So.
In the corner of we don't know. No.
Okay. So.
Can you just spend some time with her?
Thank you.
That's thanks.
Yeah.
So our next speaker, we will hear from Diane from Liaison.
Hello, my talk is about recent results from diabetes. This is the reactor antineutrino oscillation, the oscillation probability. You see, at the short baseline, about 2 kilometers, the oscillation is the delta M square E dominant. This is what diabetes were measured. At about 16 kilometers, the oscillation is dominated by the solar term. Then the reactor is the antineutrino source. It is free and a pure Nu bar source, and it has no dependence on CP phase or matter effect at the short baseline. So for precision measurement of the theta 1,3 at the diabetes, we have a large thermal power. There are 6 times 2.9 gigawatt thermal power, and the target mass is 8 times 20 kiloton. And near far relative measurement can reduce the reactor related errors. And we have 8 identically designed multiple detectors that can verify and reduce detector-related errors. And good shielding and enough overburden is also required to reduce the backgrounds. So this double collaboration, we have 42 institutes in total, 22 from Asia and 17 from North America, 2 from Europe, 1 from South America. And we have 213 collaborators. This is the layout of the diabase experiments. We have 3 experimental sites and 6 reactor cores, and the diabase cores, and the near cores, 4 near cores. That's why we need 2 near sites to monitor the reactor files from diabase and near. That's the diabase near site. The overburden is 98 meters. And near site, the overburden is 112 meters. And the far side, overburden is 350 meters rock. This entrance of the tunnel. We have multiple detectors configuration. So before this data, this is 213. That's a 680 configuration. And after this data, we have the 8 detector configuration. You can see for the oscillation probability at the near side, the oscillation probability is very small. At the far side, it is almost optimized at the maximum oscillation. This is the design of the antineutrino detector. Basically, we have 3 zoom structures. The innermost is the 20-ton 0.1% gadolinium loaded cylinder, and a 20-ton normal cylinder as the gamma culture. And the mineral oil is for the buffer shield. And we have top and bottom optical reflectors that can double the effective photo coverage. That's different to the double-choose and Reno. And we have 192 8-inch PMTs that can collect about 116 photoelectrons per MeV. So we have 8 such identically designed detectors which can reduce the systematic uncertainties, such as the target mass of the detector and the detection efficiency. The relative uncertainty is very small. This figure shows the inverse beta decay reactions. That's the design of the mu Vito system. Basically, we have 2 independent systems. One is the water Cherenkov detector, and another is the RPC systems. For the water Cherenkov detector, it's divided into 2 layers, the inner layer and the outer layer. They are separated by Tyvek. And the water is also for shielding. We have 288 PMTs in each near hole, and more than 300 PMT in far hole. For the RPC modulars, there are 4 layers above the water pool to tag the muons. And the modular number is 54 in each near hole, and 81 module in the far hole. We also have 2 telescope modulars in each hole. This is the timeline of the detector installation. So in August 2011, we installed 2 antineutrino detectors in the EH1, and in November 2012, we installed 1 antineutrino detector in EH2. EH1 is the diabase side, EH2 is the near side, and EH3 is the far side. We installed 3 antineutrino detectors on December 2011. Then we begin the 680 data taking. It is more than 200 days. Then we stop the data taking and install the number 7 and number 8, the last two anti-neutrino detectors in EH2 and EH3. Then we start the full 8 AD configuration data taking after October 2012. That's the improvement of the energy calibration. The figure shows the relative energy scale for the latest 6 plus 8 AD period. It is less than 0.2 variation in the reconstructed energy between the 8 ADs. This value was 0.35% in the 6 AD period between 6 detectors. This figure shows many calibration sources in the automated calibration unit, and also the simulation neutron calibration on gallium or hydrogen, and the monogenic gamma nice, and the alpha particles from the radioactivity. This is the energy non-linearity calibration. There are two major sources of non-linearity. One is the scintillator response. It is modeled with Burke's law and the Cherenkov fraction. And for this response, it depends on the single gamma energy. So that's why we plot the NGD energy at between 2 MeV and 3 MeV. That's the average single gamma energy for NGD capture. For electron response, it is modeled with Monte Carlo and a single channel FADC measurement. So this is for the gamma calibration data, and this is for the continuous boron spectrum. So we simultaneously feed these two types of data to get to model our non-linearity curve. Except these two types of data, we also validate our non-linearity model with thorium and bismuth beta decay spectrum, and also the visual electron spectra from the muon decays, and the scintillator quenching measurement using the neutron beams and complex scattering electrons. This experiments in our laboratory. This is a whole picture of the diabase data taking. So for the analysis data set, divided into two periods, 6 AD period, then more than 200 days, and 8 AD period. The analysis time is more than 400 days. But currently we have new data almost larger than 400 days. So in total we almost collected more than 2 million antineutrino events. There are 3 past oscillation results shown here. The first 2 is red-only analysis to measure the theta 1-3, and the third is the red plus shape analysis to measure theta 1-3 and the delta square EE. They are published, and this talk will focus on the latest analysis, the 6 plus 8 AD combined NGD theta 1-3 analysis. It is 621 days, and 6 AD absolute reactor flux and spectral measurement. And the last 2 results have already been published. The 6 AD NH theta 1-3 rate analysis and then the light stereo neutrino search. So this is the antineutrino candidate selection. First, we reject the primitive flasher backgrounds, then applied the muon veto. There are 3 types of the muon vetoes. One is the water poor muons. I mean the muon is tagged by the water channel detector. Then we reject 0.3 microsecond. And the AD muons, we reject 1 microsecond. The mu goes through the AD and we have 20 MeV energy deposit. And the AD shell mu, that means the mu deposit much more energy in the AD. Then we reject 1 second. This figure shows the energy cut for the prominent positron energy and the delayed neutron capture energy. For the prominent is 0.7 to 12 MeV. For the delayed is 6 to 12 MeV. Then we applied the neutron capture time cut from 1 microsecond to 200 microseconds. So this figure shows the neutron capture time both for the data and the Monte Carlo. You can see the agree with each other very well. And at last we applied the multiplicity cut. We only allowed the isolated candidate pairs. That means there are no singles around our selected pairs. Here is the efficiency of this selection count. So in total, the combined efficiency is 80.6%, and the correlated uncertainty is 2.1%. So this correlated uncertainty is for the normalization of all the attenuation detector. This is the uncorrelated uncertainty between the eta detector is only 0.2%. So this figure shows the IBD rate versus the time. So for this analysis result, we have more than 1 billion antineutrino interactions. So the first, this panel is for the diabetic site, and the near site and the far site. You can see the predicted rates and the observed rates are consistent. This is a background budgets. We have 5 types of background. The dominant is the accidental background. The ratio to the singular is 1.4% at the near site and 2.3 at the far site. However, we can precisely measure these types of background by precisely measure the rate of the singles. Then the uncertainty of the accidental is negligible. And for the Eastern-9 and 108 background, it's 0.4% both for near and far side. The uncertainty we assign 15% uncertainty. It was measured with the alpha mu events. And for fast neutron backgrounds, 0.1 both for near and far side. And the uncertainty is 30%. It was measured from the RPC and out-of-order short tagged mu events. It is different from our previous result. In our previous result, we just we use linear extrapolation based on this energy spectrum. Extrapolate the spectra larger than 12 MeV to below 12 MeV. But now we use this tagged events to predict the fast neutron background. And for americium carbon sources, it is 1/3 of the previous result. Because we take 2 sources from the far side ADs. This is the 3 calibration units. We take 2 sources out of these units. And for alpha background, it is calculated on the major radioactivity. And the method is same as before. This is a summary of the data. This is for the 680 period. This is for the 880 period. So in total, we have more than 1 billion antineutrino events collected. You can also see in one experiment hall, such as the 81 and 82, the IBD rates are consistent. Except for the red consistent, we can see the spectra is also consistent. This top two figures for the EH1, 81 and 82. For the prominent energy spectra and the neutron capture spectra, you can see the ratio of the spectra is flat. This means that in addition to the red consistent, the spectral shape is also consistent. The expected ratio of the 81 or 82 rate is 0.982, and the measure is almost the same. For the EH2 side, the spectral shape is consistent too, and the expected ratio is 1.012, and the measure is 1.019. That ratio in one experiment hall is not one because the baseline difference is several meters for these two detectors. So the expected is not one. This figure shows the red deficit and the spectral distortion. This figure shows the red deficit of the far hall to the near hall. So this a relative near to far measurement of the oscillation. And for this figure, this dot is the far side data, and we combine the two near side UCR data to predict the far side spectrum. You can see there's a clear spectral distortion like this. And we can also see the observed data is highly consistent with the oscillation interpretation. This is the oscillation results for the sin square 2 theta 1c and the delta square E measurement. The figure shows the contours for 1, 2, 3 sigma. And this value, the uncertainty of the sin square 2 theta 1c is 0.005. And it is currently the most precise measurement. The uncertainty is 6%. And the delta square E is also the most precise measurement in the electron neutrino disappearance channel, is 4%. We compare this delta square E measurement with the MINOS and T2K measurement. You can see the value is consistent with these two mu neutrino disappearance experiments, and also this uncertainty are comparable to these two experiments. This absolute reactor flux measurement. So we measure the reactor flux and show in this figure. You see the measurement of the 6 eddies are consistent. And then we get the average value. Then we get our data over predictions. We compare this value to the the predictions. We have two predictions. One is the Huber plus Mueller prediction, and the old year plus Vogel prediction. You see this data over prediction is several percent from 1. We plot our measurement. This data point is double measurement. We compare this value with the previous shorter baseline reactor measurements. See, they are all consistent with the reactor flux anomaly. Then it's the absolute spectral shape measurement. We can see the absolute spectral shape is not consistent with the prediction. We can see a significant bump in the around 5 MeV, a significant bump. Since the Huber plus Mueller model maybe it still have some problem, but this topic will be covered in Dan's talk tomorrow. After we get the primary energy spectra, we unfold this spectra to the antineutrino energy. So this may be another way to precisely measure the antineutrino spectra. One is based the IBD primary spectral measurement. Then we get the antineutrino spectra. This data contains this data set. This IBD contains is over 2 million events. And the previous model prediction, this data basically come from the beta spectral measurement. This independent theta-1,3 measurement through the NH capture. As we know, if the neutron captures on the hydrogen, then 2.2 MeV gamma emits. The key features are it has a high statistics. So addition, we have additional 20-ton liquid centimeter target per AD. And the systematic uncertainty is also different from the NGD analysis. So it is really an independent theta-1,3 measurement. But the challenge is we have very high accidental backgrounds because we need a longer capture time and a lower detector energy to include the 2.2 MeV gamma. It's shown in this figure. This is all candidates, and this is the accidental background. This cluster is the NGD event. This peak is for the NH event. You will see this cluster are almost the backgrounds, accidental background. After subtraction, we get the dilated energy spectra like this. Previously, we cut at 6 MeV to get the NGD events, and currently we select this energy peak. Our strategy is we raise the primary energy cut to 1.5 MeV, and we require the primary to delete distance cut smaller than 0.5 meters. That's the result for the NH analysis. So for the full 680 data, the result is 0.083, and the uncertainty is 0.018. This is the radar analysis measurements. It is another precise measurement of sin square 2 theta-1,3, and it dependent with the NGD result. From this figure, we can see the spectral distortion is consistent with the oscillation explanation. This is very nice, the oscillation prediction. This data point is consistent with this line. And the spectral shape analysis is in progress. And search for light stereo neutrino. If there are light stereo neutrino, this is the oscillation probability. Then we have another oscillation mode in addition to our the sin theta-1,3 oscillation. So that will provide a unique opportunity for stereo neutrino search because of its unique baseline configuration from 3 experimental sites. We studied the sensitivity of the to exclusion the stereo neutrino. We found that between 10 to minus 3 eV square to 0.1 eV square, W has a very good exclusion power. This region is not explored before. This is the result for the 680 data. We found there's no significant signal observed. It is consistent with 3 flavor neutrino oscillation. So we set a mostly straightened limit at this delta square range. So this is the summary. We have high precision measurement with 621 days of data. This shows this uncertainty of the sin square 2 theta-1,3. The precision of both sin square 2 theta-1,3 and delta square EE is expected to be 3% by the end of the 2017. We also have many other analyses carried out precise measurement of reactor flux and spectrum, and independent measurement through an NGD captures and search for net stellar neutrinos. So thank you. That's all.
Please, go to slide number 16.
16.
Okay, so we know that there is this bump up by MEV.
Yes.
How do you correct for this?
Correct. We did not correct. We use a relative shape to far to near. Then the boundary is the same for far and near side. For relative, there is no bound.
I mean, this will introduce some systematic error, right?
No,
In the evaluation of the data
has
square.
That has a negligible impact on the oscillation measurement. Yes.
One more question.
So what's the amount of 5 MeV excess compared to 2011 Huber and Miller model?
The excess, how many the excess?
So what's the excess amount?
The amount is about 2%. The amplitude is about 10%. See the amplitude is 1.1.
Excuse me, you said 10%?
The amplitude is 10%. The amount is about between 1 and 2%.
2%.
Yes, nearly.
But you don't have number, just the few
Yes,
percent.
I don't have a number on side.
We reconvene here in 15 minutes at 4:35.